Welcome to Advanced Word Normalization with MySQL Proxy. My name is Roepke. I work for the MySQL Enterprise Monitor I. We do monitoring and proxy. Let me start off with where we're at now. MySQL Proxy is on Launchpad. It's under active development, contrary to any rumors. Currently we're two developers, Jan and me, and one QA guy. He's not here, Diego Medina, I know from the mailing list, and we're still trying to grow the team. Might be a bit difficult, but we'll try. MySQL Proxy is the basis for the query analyzer. Still can't get over the name. It's just basically query analysis, which is way easier for me to say. And for me personally, it's very important to not think of MySQL Proxy as a proxy, because that has this connotation of just something coming in and we're sending it forward. But it's actually more of a middleware that can do pretty exciting things with it. It's scriptable, so there's a lot of things you can actually do if you really care and really want to. So common use cases of proxy, you are probably very familiar with them, but I still want to go over them. There are a couple of connection-based things you can do, for instance, load balancing or accounting. There are more, but those are the common ones. And the more interesting ones are query-based. Again, accounting, based on individual queries. Say, how many rows did I access in this table? Something like that. Quota-based. You can do sharding. You can make sure that queries are safe. So, for instance, can deny deleting from certain tables or certain rows. Query analysis, that's what we do. And my favorite, read-write script. So there's actually a common denominator with all of them. Especially I'm focusing on the query-based ones right now. For one thing, we need client and server metadata. We have that. Proxy is aware of that, knows the protocol. And implicit connection state. So all this stuff you can set to MySQL, which makes it really hard to interfere with it, because you can change SQL mode and that changes all kinds of things. But even if we have all that, and we actually do right now today, it's very hard to reliably fill with the query text. So if you just have the string, well, it could be uppercase, could be lowercase, or star, and could contain an arbitrary amount of white space and quoting and all kinds of fun stuff. But we found out that this very simplistic tokenizer lexer brings you surprisingly far. And that's what we right now use, and well, we can pull off query analysis with it and non-line queries. But for some things, it's just not far enough and not enough. Here are a couple limitations. I picked the three probably most popular proxies out there. All of them are here at the conference, and there's talks on all of them. One is domainless proxy, MySQL. It doesn't contain any tokenizing defined, which surprised me. So I saw a lot of subscript. And of course, it doesn't have a tokenizer, so it doesn't have a parser. The parser is the next step once you tokenize the actual text. The other one is Spot Proxy. As you might know, it's a fork of MySQL Proxy. They stripped out the lower layer, and they concentrate on sharding. So it's a pretty special purpose, and since it's a fork of MySQL Proxy, they also inherited our flex-based tokenizer. But there are some fixes we did that weren't important yet, so you might want to watch out for them and tell them. And I haven't seen them yet, so just and it contains a fuzzy parser, so it's not really a strict one, but they look for certain telltale signs in the text and try to reconnect stuff. So say they look for update and try to make sure certain keywords are there. For instance, set. it is obviously pretty fast because you don't really actually parse it, but you know, still feels a bit like a hack. We do that too. Which brings me to MySQL Proxy. Obviously, same thing, flex-based tokenizer. It has no shortcomings. We are aware of that, but it does the trick right now. And we have a minimal parser that is written in Lua and using LPAG. It's a parser expression grammar that's tagging it. It's actually pretty powerful, but it takes a bit getting used to. And since it's all in Lua, it's not the fastest thing in the world you can imagine, but it's actually pretty good. So I thought, well, how about a new approach? How about actually having a complete solution for flexing, parsing, and manipulating the query text as it comes in? There's some interesting requirements we had. We developed query analysis. We wanted to do this highlighting, this fancy, show me what my query actually looks like, indent it and highlight it. So, well, the MySQL tokenizer and parser was out of the question because our monitor application is written in Java. And I'm not going to interface that with JNI and try to do that. So it has to be portable even across languages. Should be easy to debug because parsers can screw up pretty badly. And third thing is it should be embeddable into other applications. So it'd be great to just take the library and reuse it in some other open source application. For instance, it looks pretty nice for Workbench. Workbench actually did a different thing that took the MySQL parser and cleaned it up. But as I said, it isn't portable across languages, so it was out of the question. And well, I'm biased, so I'm contributing to the ANTLR project, which is a parser generator. Stands for another tool for language recognition, kind of play words. And yeah, and that's what I did. Let me give you just a little brief overview of it. As I said, it can generate code in many languages. It has a code generation phase and uses string templates to actually generate the code. So the currently working ones that are in the latest version and tested are in Java, C, C#, and Python. And that, as you can see, that's pretty flexible. So you can start with your one grammar and just change the language parameter and get the same thing in different language. It has an IDE, comes with a debugger, which is very handy. You can set breakpoints and unrules. And it integrates Lexis, parsers, and pre-parsers. I'll come to pre-processing in a bit. Through the same language, the same grammar language. So it is actually just one tool. You don't have to use Flex and Yak or Python or any other kind of things. Just one language, integrates nicely, just makes it life easy. And as Python, it allows for hardware reactions in the grammar itself, so you can actually do stuff with it. So that's custom code. You can put that anywhere in the grammar. There are other parser generators that don't allow you to do that because of the algorithm they use. And it's a recursive descent parser generator. So you can actually read the code that comes out, which I find very, very nice, especially if you want to debug your actions. So you can go in there. Well, the source files are huge, but still, they're pretty readable. That's actually what you would write if you hand code a recursive descent parser. And it's got this neat little trick. It is LL, so top-down recursive descent. And usually you have a fixed amount of look ahead. So look ahead is the amount of tokens you can actually look forward in time, but in the text or in the token stream, and to decide which rule you have to call to actually parse it. And most of the parser generators have a fixed amount to look at, which sometimes makes it very hard or unnatural to write grammar. And this ANTLR has a special algorithm that's called LL star, obviously for infinite or arbitrary amount to look at. And that makes it, at some points, really, really easy to write grammar. And well, yeah, I'm working on MySQL Proxy, I'm working on ANTLR, and my realization was we need a real parser and full lexer to do query manipulation in a safe way, in a fun way, I think. Well, actually, as I said, the MySQL D1 was not, we could use it. Just separating it out from the MySQL server itself would be a pretty big feat. And then keeping it up to date wasn't exactly fun either. So, the Lex is handwritten in MySQL, so that's another complication. MySQL Proxy is in C, and MySQL is in C++, and it's in Yaml. Well, kind of touched on the point. I want maintainability in something like this. It's pretty complex piece of code. You have to maintain it over time, especially if you want to support multiple versions of the MySQL dialect. It's always fun. I wanted to have a clear grammar. Just looking at the MySQL YAT grammar is just a nightmare. Just trying to follow through where stuff goes is just not fun. So ANTLR has this debugger, and you can actually look at it. And I want to be able to extend it pretty easily. So what do we want in proxy anyway? We need to be able to tokenize the query. Sometimes that's enough. We need to parse the query, so we need the tree, the syntax tree, which should be stable. And to do the fun stuff, we actually need symbols. So we need the table names, the columns, etc. And then we kind of have to work with the tree. Just having the trees doesn't get anything done. So we need to get subtrees. We need to be able to replace those and get the string back. Here's some. That's for the rest. Here's some example code how you can use the new tokenizer in it. It's really simple. You just if there's an import missing, actually you have to import a library, obviously, which is called parser. You just initialize that and ask it for the table of tokens, array of tokens, and then we can just print them on. I'll show the example later. We can actually see what's going on there. It's pretty straightforward. You don't really have to do it. What information do we get from a token? For starters, its name, or for instance, select token. The index into the token stream. So ANTLR operates on streams. You give it a character stream, which mostly is being filled by from a string. Then you call the lexer, which produces the token stream. You can skip around and do all kinds of things in there. And the parser actually creates a tree node string, which creates trees. Take a look at that too. Obviously, we can get the text back for token. And every token has a channel. I'll show that in the next slide what that means. It's kind of a neat trick. And of course, the position of it. Line of the first character of the token and the position in line of the first character. So what's the channel? In a way, ANTLR is like a radio. You can assign a number to any token, and by just assigning that number, you place it on a channel. And parsers can tune into that channel. That's great for tokens you want to preserve, but you don't actually care about because they don't carry any semantic information, like white space. If you want to get the actual input string back, you want the white space. But if you parse, you don't. And it is pretty neat. And at one place in the MySQL grammar, you actually need the white space to bridge between functions. It's a pain. And comments are same thing. We have these special version comments that actually can turn on or off certain things depending on the server version that executes it. So we want to see them too. But not the others. It's better than anything else. So what do we have to do to parse a query? Again, very simple. We have, well, that's a copy-paste error again. Recognize it should be the object we got back when we tokenized the query. So we just tell it, well, let me give the tree, give me the tree, and you have two options on there. You can either just get the entire text back, that's the low one, just access text, or get a tree string, which is the list notation of the representation of the parser string, or abstract syntax string. That's nice for debugging or showing up. And well, great. Now we have the tree, so great. Can't really do anything with that. So what does the parser actually do? Its purpose is to validate a sentence in the grammar, or input against the grammar, if it forms a sentence in that grammar or not. And in this implementation, I chose to not actually execute anything, any custom code during parsing. It is possible to do that, but if you do it, you kind of limit your options, because the underlying parser implementation I used is in C. So you don't really want to recompile proxy all the time and change it. Just the reason it has low in the first place. So instead we built an abstract syntax tree. An abstract syntax tree is called abstract because it's not supposed to depend on the form of the grammar. So if you rearrange a couple of parser rules, it shouldn't affect the shape of the tree. So that's what's abstract. The opposite would be the parser tree, which is the one-to-one representation of what rules were executed to actually parse it. Well, trees. Speaking of trees, luckily ANTLR supports trees directly. And usually you deal with lexing and parsing, you tend to write a lot of visages for those trees by hand, which, well, again, you're hard coding in some language. MySQL idle tree is one example of that. It's great during parse time, and there's all sorts of stuff that operates on that tree. You actually have to know how that tree looks like in code, how it works together, and how it ties together. But we don't want to hand code, and we don't want to hard code, at least not this stage in the code. So we want the flexibility of Proxy to be the thing that we actually thrive in. So let's use ANTLR's tree parsers. And tree parsers are, as the name says, grammars for trees. And they validate tree input, so they validate the shape of the tree. And since they're just ANTLR grammars, you can again attach code to them. But now you're at a pretty condensed point of the input string, and it doesn't refer to any text. So it becomes much more easy to actually rely on the stability of that. And well, as I said, ANTLR is pretty stream focused, so parsers consume one-dimensional streams of tokens, and tree parsers consume two-dimensional stream of tree nodes. Well, a tree is not one-dimensional, but actually it is, of course, in the implementation. So all it does is includes up and down nodes. It says, okay, you have to go up this in this tree or down in this tree to bracket shelter. If there are any questions, going fast, please interrupt or throw something. So how can we make use of tree parsers? There are different approaches. We can have specialized phases, specialized tree parsers for each different application, which comes back to the point of, well, it would be hard-coded, and we would reinvent the wheel all the time. And I don't want that. It's more work for me. So what about the idea to have a generic tree parser that's doing it all? Basically just does nothing. It just visits all the nodes in the tree and checks for a callback function. And this callback function you can just write in Lua, and you get passed in all the components of the tree and the root of it. Because the problem is, I don't know what you want to do with it. And if I write specialized tree parameters, you are stuck with what I say to do. And I'm pretty sure you don't want that. So yeah, it would be nice to have callbacks. So and that's one little example of it. So Lua syntax, that's basically a hash. Called callback. And the key is, in this case, show engine. That corresponds to the callback positions you can have in the tree parser. This obviously gets called back when the parser sees the show engine. And show engine has parameters. Well, it is not a parameter in SQL, but it kind of is from the language point of view. So it gets the name of the engine and the attribute you want to have. It's status and mutex. That's only really useful for NDB anyway. There's a special NDB token in there too, which is also fun. Show you the grammar. So this function, this anonymous function, gets called with two of the tree nodes. And you can ask the tree node for its parent and traverse the tree yourself if you want. You need some kind of surrounding information. Or you can just get the text for it. And this would just print, well, mutex for engine LDB. And notice that it would actually go back to the input string. So the text attributes here would actually be in that very case, or uppercase, lowercase combination of what the user actually wrote. And it doesn't copy. So, well, it copies it to Lua, but it is actually just a pointer into that first string, which is nice. Not too much of it going on all the time. And you have a tree, stable tree, V1 to probably 4. And you just set its callbacks attribute, which expects a table with keys like the callback names. And then you just tell it to walk. That's all. And at this point, I'd like to show you some examples just to get a feel for what the code looks like and what you can do with it. And if I've still got time, I can try to show you something with ANTLR and actually how to implement all these kind of things. Right? So this is running MySQL Proxy. Nice. Did you see that? Yeah. This is actually just MySQL Proxy 070 from Launchpad. There's nothing special about it. I'm using this tutorial ANTLR Lua script. It's a really simple script to just give you an idea what it is, and well, I'm setting round level, so that's not really exciting. Just get started. So let me just connect to proxy port. As root, you should never do that with one password, and to the database test. So the thing, when we switch back to the log output, we see there is all kinds of output. And while the MySQL client application actually does queries for you once you connect. So the first thing you see here is a status. Oh, that actually works. Just status log message. It has received a show databases command. And what the next things are is basically just going through the token stream and printing out all the attributes we know about. The first number is the index into the token stream through a subdomain, so that's one. Then its name, that's a token name. And you can refer to those in the, well, not yet in the Lua code, but it's pretty simple to expose that. So every token has a name. Let's show the number in there. That's just the internal ID, token ID. It's rather uninteresting. After that, it's kind of hard to see because I failed to quote it in some way. Is the actual text from the input string. So the white space you don't actually see, so it's white or looks black. And then we have the channel information. So default channel is 0, and as you can see up there, white space is channel 99. It is still there. We didn't skip it, we didn't throw it away, so we can still get to it. And well, then we have the line information and indexes of this string. Because actually it's from C, so if you would use that, it would not work. It's a 0. Next up, I just used the tree string command. This is a rather uninteresting tree. It has one root node, and that's show. So this is this notation that we want. The first element is the root. The following things are general. We can get the text back, and we can. Oh, that's nice. Just tells me there's no subsystem there. So this is kind of neat. We get the text back, and then we get a critical warning, which wasn't intended to be there. Show tables, same thing. And this gets more interesting actually. The client does a select version comment, display what kind of edition you run, and as you can see here, this is much more accurate than the existing tokenizer. So it actually tells you there's no variable name. And well, they implement it in all kinds of different things, and the string representation of the tree is actually more interesting. Let's scroll that up. So there's a select root node. Select is lowercase because if ANTLR knows the input string, then it will just print it out there. Then we have a couple columns that we select. Columns is just the internal name. Obviously, it's not actually a column, but it's a select expression which says version count. And I noticed the limit is missing, so I should probably bug against myself. So this little example I put into the proposal that looked like this, pretty much. Let me show you the table, so it's really straightforward. We have one users table that's totally uninteresting. I'll show you anyway. ID in the email, and forum members are pretty much the same. They connect forum ID which, well, there's no parse table, so it's pointless, and a user ID. And in cases where these tables actually don't live on the same server, but they're sharded in some way, it gets interesting because you can't just log in for the sake of debugging, and I used to do that all the time back in the day. I still run web applications. And it's a pain. You can't just log in to a single place and, well, do that self-select or join or whatever, because the data isn't actually there. So it would be pretty cool if we could reliably get the two selects in there and pull them out, do the inner select, the inner sub-select on that server that actually knows what the data is, and then just substitute the user IDs we get back into the other query and then execute that on, well, the corresponding database. So just let me run the query and we have to get out. So I noticed that my email address was there, hi@sun.com. I failed to put that into the slides. Made it up. And this is actually what you would expect. So it's and that data is actually correct. I can show you the tables. They're small. But what it did in the background, there's some debug output in there. Well, this is kind of pointless. This is just, you wouldn't do that normally, but this is for demonstration debugging. So it dumps the entire token stream. And actually, this is a fun kind of tree. I have a collection of ugly syntax trees at home, so just collect those. And this is how the tree actually looks like. So it takes a bit of imagination to actually see a tree in there, but you stare long enough, and it's drawn. There's some output scene field ID, email ID, user ID that doesn't make any sense until I actually show you the script that does it. So we used to have, let's solve this stuff. These are sample callbacks I wrote just to give you an idea of how it works. And what we have seen in the output is this one. It doesn't work. So we just say whenever you encounter a field, which probably is a column or a variable or a constant, please call this function. And he calls it with the subtree that's in the field, or that represents a field. And we just print the text out and use closure columns. That's up here, just a hash. And we can basically implement a full-man simple table using that. We can index by the actual text of the field we're selecting, and point back to the tree line. Just gonna notice that all of this is just Lua. So there's nothing in C that tells you how to do it. You just come over. Obviously, you shouldn't have to, and we should provide the infrastructure for it. But this is the start. So, and things get actually more interesting if you look at select and sub-select, where you have all kinds of arguments there. The select, the first parameter is actually the entire node, tree node, root node of the select. And the other ones are the possible things you can have attached to a select. So there's options, there are columns, there's a from clause, which can also contain select. There's a web clause containing expressions, group by, and so on and so on. And here we just collect them. This is a funny Lua notation to increment the index. It's just an array. So if we look back at the output, here's actually what it found out. So it found a subselect in there, which is true because there was a subselect in there. And if we go back to the actual query, we find, yes, that actually was the subselect we put in. So it works. I was very glad to see that. Great. There's some, well, this is rough, really. And here we're injecting the query. This is standard proxy code. Really, we have a read query callback function that just gets the query text out of the packet. Calls handle query. Handle query is basically all this code here. What all it does is initializes the parser, gets tokens, and actually gets trees, or the tree, and returns the first subselect. So we get back the tree containing the subselect, and all we do is append the query. So we can inject the query. Obviously, at this point, this runs on the same backend, so you could really chart it, but the point is there. You could actually use that and connect it a different way. We just insert the entire text and tell proxy that we actually do care about the results and don't want proxy to simply forward to the client again. And when we get called back, we look for this query, we inject it, collect the rows. We know at this point, this is a very simple example, not very flexible. We know it's just going to be one column. Just collect all the IDs. Then we peel out the subquery. Basically, just remove it. Ideally, this should set the tree to nil or null. That didn't quite work because we're at that point walking the tree and might actually be under the tree, and when we walk back up, crashes. So we're working on that still. And take the original statement. There's still the in and out in the new statement. From the previous one, I can show you the output in a second. And just concat all the IDs together, and then append this query again, which will give us the actual result set. And well, that's what we're gonna send back to the client. And to show you that it actually did it, this is the query it ran after parsing out the subselect, executing the subselect, and then pulling that back together and executing the second query. Great.
Can't believe you ever reporting right now.
We're still running out of time. 2 minutes left, I guess. So this is basically where we're at right now. I'll be pushing the code to Launchpad today, so we can actually go and play with it and break it, and please tell me that it's still kind of close. Any questions? Comments? Please? So the question is, would you be able to run the subselect on a different database rather than the same backend? Is that correct? Or database as a different database host? Yeah, you could do that. Yeah. So what is the point of doing the sharding? You can actually pull that out.
Make the assumption you run MySQL Proxy on the same server as MySQL team. What kind of performance impact running MySQL Proxy will you get?
The question is, what kind of performance impact does MySQL Proxy have if you run it on the same database host? That depends. Right now, it's single-threaded still. We have a runtime implementation we're working on for the network multi-threading. So right now, it really comes down to what your queries look like and what the parameters are for your queries. So the smaller the execution time is and the smaller result sets are, the more overhead we will have. So in the worst case, we've seen 50% overhead, but that's really the worst case. And customers using the query analyzer tell us that generally it's 10 to 50%. So the question is, how many commercial deployments do we have with MySQL Proxy? That probably comes down, I see Mike there.
Well, I'm started working on the project management with the Proxy has.
So,
But
so the Enterprise tool 2.0 is using Proxy, so everyone who's using query analyzer actually uses Proxy.
But you were meaning other ones.
Well, I know at least 3 customers who use Proxy in production today. It's kind of hard to get actual numbers because it's open source project. Not everyone tells us. Unfortunately.
I was using MySQL Proxy on the production side because it gives copies of the deal with that. And so I get the file on many quite a lot.
Great. That's it. Any more questions? I should probably wrap this up. Okay. Thank you for coming.